In this video, we're going to talk about the fate of low to medium mass main sequence stars. So to put it in perspective, we have the stars that are really small, like brown dwarfs that never fuse, or red dwarfs that fuse but perpetually always get stuck in the main sequence phase because they never run out of hydrogen. We're going to talk about the ones that do run out of hydrogen in their core and what happens to them. That comes out to be about 8% the size of the sun's mass, up until about 4 times the size of the sun mass. So the sun's, steadily in the middle of the group that we're going to talk about today. Just to remind you where we left off, all stars start as a dark nebula. Something causes it to contract, and when it gets hot enough to glow, we call it a protostar. Protostars accrete or gain mass until they start to have a little bit of resistance and the rate of accretion slows down. At that point, we call it a main sequence star. And finally, main sequence stars are stars that begin to fuse hydrogen in their core and reach a hydrostatic equilibrium. In other words, they're no longer gaining mass anymore. To understand how stars evolved past the main sequence, it's important that we have a little bit of understanding of the anatomy of a star. We don't want to get into too much detail, but essentially, there are 3 areas of the star. The core is the inner part that first does fusion. The shell is the area around that. That's what we call convective, and that essentially means that the material in it is flowing due to density and temperature differences. And then the outermost area is the envelope. That's the portion that never fuses. It's much, much less dense. And that part is the part that radiates energy out to the rest of the universe. And remember, in that inner core, the hydrogen is fusing into helium, and the helium is accumulating. However, as the helium accumulates, to fuse a heavier element like helium, it requires a lot more energy, a lot more heat. And the main sequence stars in their core don't have enough energy for that yet. And so the helium accumulates. As more and more hydrogen turns into helium, there's less fusion going on because there's less hydrogen to just squeeze together to interact with one another. And so the constant battle that's occurring inside of a star between gravity collapsing it and fusion and other forces pressing outward starts to have instability. Instead of being at a hydrostatic equilibrium in the main sequence, instead the core starts to contract. As the contraction raises the temperature, it's still not hot enough to fuse hydrogen into helium, but what it is hot enough for is to make the area around the core, the shell, hot enough to fuse. So remember, it's got to reach 10 million degrees Kelvin to fuse hydrogen. Previously it wasn't, but due to the contraction, the shell begins to fuse hydrogen. That new fusion now provides an outward pressure. That outward pressure is actually further out from the center of the star, so that not only does it provide a resistance to the gravity, but it actually causes the outward pressure to expand and win the battle and expand the size of the star because it's further away from the core. There's less gravity there. The star expands, getting much, much larger. At that point, we call it a giant or a supergiant, depending upon the mass of a star. The ones we're talking about today are going to be called giants. So if we take a look at this diagram of the star, inside the core we have a lot of our helium. This area in the shell is the area that gets hot enough for fusion. That's fusing hydrogen into helium. The helium being produced is turning and being dumped into this core. And finally, we have this outer area that is radiating the energy outward. And because of all this pressure from the fusion, that envelope is expanding. So why is it red? Well, the surface of the star is getting further away from the area of heat. And because it's getting further away, imagine that you are standing around a bonfire. The further away you get from the bonfire, the cooler it feels. It's kind of a similar phenomenon. Because the surface of the star is farther away from where the center is, it actually cools off a little bit. So even if the star was warmer, like our sun, which is yellow, the star will become orange or red, usually red at this stage, as the surface expands due to that shell fusion and cools down. Earlier you labeled this left side of the diagram in your notes. Now is a good time to label the parts of a red giant star. So we have inert, in other words, non-fusing helium in the core, and fusing hydrogen in the shell. Finally, before we move on from the red giant, to just kind of take a note, we were talking about stars that are on the main sequence. Where they are, remember, depends upon their mass. The area of the stars that we're talking about are somewhere between the red stage and probably up into maybe about there in the white area. And those stars, as they move off of the main sequence, in other words, as they evolve through the red giant stage, are going to get cooler, so they'll head towards the red, and they get larger, which means that they're brighter. So they'll move up to the top right area of the HR diagram. Recall in the red giant stage that the shell is fusing hydrogen into helium. As the shell produces hydrogen into helium, the helium ends up in the core and it contracts and gets hotter. That additional heat finally reaches the temperature needed, 100 million Kelvin, to fuse helium. When helium fuses, it can make carbon and oxygen, depending upon which nuclei interact with one another. And again, that's possible because helium from the shell gets dumped into the core. That increases the gravity, causes the core to collapse and make more heat, and that additional heat leads to fusing of helium in the core. Sometimes in some stars that happens very, very quickly. It's called a helium flash. I don't really need you to worry about that right now. The helium fusion in the core stops the expansion that was happening in the red giant stage, and the envelope starts to contract. That contraction leads to the envelope getting hotter. The envelope getting hotter then causes the star to change color from the cooler red to a hotter color like orange or yellow. Because it moves essentially from red over to yellow, basically horizontally. It doesn't increase in brightness all that much. We call it a horizontal branch star. Because it's yellow and it's still very large, sometimes we call it a yellow giant. Now, in a yellow giant, again, the most important thing that you can get from all of this is that in a yellow giant, we have fusion happening in two places. There is helium fusion in the core, where it's making carbon and oxygen, and hydrogen fusion in the shell. You have this diagram in your notes. Please make sure that you label the parts. Our next stage is called an AGB star, sometimes known as the second red giant star. The reason why it's called that, number one, is it becomes another red giant, but number two is the process that forms the red giant the second red giant is very similar to the process that forms the first one. So in this case, just prior to this, in the yellow giant stage, we had helium making carbon and oxygen in the core. Just as we've seen before, the core isn't heavy enough to fuse the heavier elements, and so the carbon and oxygen accumulate in the core. With the reduction of material to fuse, the core contracts. That contraction causes the area around the core to warm. That makes the shell warm enough to fuse the helium that's there, and we get a new area of fusion. Sometimes, again, that can happen very, very quickly, sometimes called a helium flash. Other times it happens much more slowly. You don't need to worry about that. But what is important is now we have fusion happening in the shell. That new fusion in the shell, just like we saw before, presses the envelope out further. Moving the envelope out further causes the surface of it to cool, and the star moves to the right on the HR diagram as it expands. So again, because it's a red giant again, sometimes we call it a second red giant. Scientists also call it an asymptotic giant branch star as well. Carbon and oxygen have accumulated in the core. It's run out, there's no fusion happening there. But nearest the core, the helium that's there in the shell is fusing into carbon and oxygen, dumping its carbon and oxygen here. So we've got a layer of inert, in other words, non-fusing carbon and oxygen. And then we have a layer in the shell of helium fusion, and a layer outside of that of hydrogen fusion. That fusion, which is close to the surface, is expanding the outer envelope outward. The force of gravity is pulling in, but not as strongly as that expansion force, and so the star is expanding and becoming larger but cooler. And because it's becoming larger but cooler, it's moving over here to the right on the HR diagram. Recall that in an AGB, or a second red giant star, there's fusion happening in the shell. The fusion is dumping its products into the core, and the fusion is causing the outer layers of the envelope to expand. That expansion eventually leads to the death, if you will, or perhaps the retirement of the star is a better term. And that happens in the formation of what we call a planetary nebula. So the planetary nebula forms from the outer layer, the envelope of the AGB star. It happens in stars like the medium-sized stars that we've been talking about, like our sun. And basically what happens is, as the fusion occurs in the shell, material in the envelope just keeps getting pushed outward and outward and outward. Eventually, the outer layers are no longer tightly bound to the core, and we get a cloud instead, and that cloud is a nebula. We call it a planetary nebula because of a misconception astronomers had when they found it, so don't have to worry, it doesn't have anything really to do with planets, but the name stuck. So a planetary nebula is essentially the outer envelope of a star that's in the red giant phase that just has expanded outward and outward and outward. It's basically ionized gas. It's really pretty, and again, it has nothing to do with planets. These are all examples of planetary nebulas. At the heart of each one of these nebula is the dying star, the core that remained after the envelope got pushed out. That core is what we call a white dwarf. So we had the fusion happening. The fusion that was happening in the shell. Hydrogen was producing helium, which was being dumped into inner layers. The helium was fusing, producing carbon and oxygen, which was being dumped into the core. But the core was never hot enough to fuse carbon and oxygen, which requires way more energy than is possible given the mass of the star. And so that carbon, because the mass doesn't have sufficient gravity to make it hot enough, can't fuse. So that carbon and oxygen is just ultimately a super dense collection of inert or non-fusing material. White dwarfs, because there's not any fusion happening, technically we wouldn't really call them stars. They're more like the end stages of stars. Because there's no more outward fusion, the gravity is winning this tug of war that's been happening inside the star, and so gravity is now much, much greater force than the outward pressure, and the gravity causes the carbon and oxygen ball to collapse in on itself. This makes it very, very dense. A teaspoon of it would weigh about 11 tons. The gravitational energy is converted to thermal energy because, again, it's super dense and all the particles are interacting with one another, and so it's very, very hot. Still not hot enough to fuse carbon and oxygen, but very, very hot. The material can't get any closer because the electrons are repelling it. It's as dense as it can be without some additional things happening that we'll talk about later on. That resistance, though, because the electrons are repelling one another, that resistance prevents the star from collapsing, and what we're left with is this inert, incredibly dense ball of carbon and oxygen. It glows, but it's so small it's quite dim, and so it's on the bottom of the HR diagram, even though it's very, very hot. In our analogy of stellar life, this would be kind of like the star retiring and dying of old age. It stays like this for a very, very long, long time. In fact, we're not even entirely sure what happens. It's theorized that a white dwarf might eventually convert all of its energy and stop glowing. We would call it a black dwarf, but there's not been enough time for that ever to happen, so we're just theorizing what might happen. Recall that white dwarfs, as they're very, very dim, but also very, very hot because of that degeneracy pressure and that heat that's coming from the core, we would find them down here. So what we've talked about in the last video and this video basically describes the evolution of our sun. Our sun is currently in its main sequence stage, and we're about 4.5 billion years old. Eventually, it will reach red giant stage and then go through yellow giant, second red giant, and ultimately fizzle out as a planetary nebula and a white dwarf. Very quickly, I just want to talk about some of the possibilities that could happen with stars that are of this size and character. And one is that they could be part of a binary star system. A binary star system, remember bi means two. So a binary star system is when there are two stars that orbit very close to one another. They would circle one another due to their gravity. And if they are very close to one another, and they're not exactly in the same stage of evolution, it is possible that when one of the stars becomes a red giant, if the other star is a white dwarf, that material would expand close enough to the white dwarf that the gravity of the white dwarf would pull in that material, They would get extra matter from their companion, and that material is probably going to be hydrogen because hydrogen is the most abundant material and it's what makes up most of the shell. And so that hydrogen, as it encounters the hot red dwarf, would get hot enough to fuse and would suddenly have a violent explosion from very, very sudden fusion. We call that a nova. So again, novas happen when there are two stars that are very, very close to one another and in different stages of their evolutionary development. If one of the stars has already reached white dwarf stage and the other star moves from its main sequence to its red giant stage, as it expands, some of the layers of the envelope might get captured by the white dwarf's gravity, and that envelope, which is mostly hydrogen, would get hot enough, it would get close enough to the hot white dwarf that it would cause a sudden burst of fusion, what we would call a nova. So this video had a lot of information in it, and a lot of really complicated, hard to remember stuff, and most of it I don't really need you to worry about. A couple of big ideas, and that is if fusion stops, then the balance between outward pressure and inward gravity becomes unstable and the star contracts. Remember that if new fusion starts, the star has more outward pressure and the star expands. So if we apply that to evolution of a low to medium mass star, remember it made it to the main sequence where it was turning hydrogen into helium in the core. The helium that collects causes the star to contract, get hotter in the shell, start fusing and expand. The expansion cools the surface, which makes it red. When the helium in the core gets hot enough, the core starts to contract. That warms it up, which makes it yellow. When the helium produces carbon and oxygen in the core, which can't fuse at these temperatures, it contracts. Helium in the shell gets warm enough to fuse, and we now have fusion in the shell that's hydrogen fusion and helium fusion, but no fusion in the core. That causes the star to expand even more. The surface once again cools. We call it the second red giant stage. And finally, the expansion due to the shell fusion causes the star to expand and expand, leaving the outer envelope to become a planetary nebula. And the dark core that remains of carbon and oxygen, which collapses due to its own gravity, is called the white dwarf. If you can get basically what was on this slide, you're in pretty good shape.